Welcome back to lecture 16. Today we're going to talk about some more object detection and as well as some different types of segmentation tasks. So last lecture, recall that we started to talk about all these different types of localization tasks that we can do in computer vision that go beyond this image classification problem that assigns single category labels to images and instead tries to localize objects within the input images. And last time we really focused on this object detection task, where we have to input this a single RGB image and then output a set of bounding boxes giving all the objects that appear in the image as well as a category label for each of those boxes. I think that we went a bit fast through a lot of the concepts in object detection in the last lecture, so I wanted to kind of recap a little bit some of the most salient points from last lecture. And one point that actually we forgot to make last lecture is just how important deep learning has been to the task of object detection. So this is a graph that shows the progress on object detection from about 2007 up to 2015. And you can see that from about 2007 to 2012, people were using and the y-axis here is the performance on this object detection data set called Pascal VOC. And the metric here is, of course, the mean average precision that we talked about in the last lecture. And we can see that from about 2007 to 2012, people were using other types of non-deep learning methods for object detection. And there was some pretty steady progress on this task from about 2007 to about 2010. But from about 2010 to 2012, the progress had sort of plateaued on this object detection problem. And then starting in 2013, when people first applied deep learning to this object detection task, then you can see there was a huge jump over all of the previous non-deep learning methods. And this jump was not a one-time effect, that as we moved on to better and better object detection methods with deep learning, then gains continued to go up and up and up. So by the way, these dots that are the deep ConvNet detection are the familiar fast, faster, and slow RCNN methods that we've talked about last time. And each one of them just gave huge improvements over the previous generation. And this led to a period from about 2013 to 2016 of just massive improvements in object detection that really overcame this plateau that the field had from about 2010 to about 2012. You'll notice here that this plot actually ends at 2016, and the reason is that after about 2015, people stopped working on this data set because this Pascal VOC data set was deemed too easy at that point. So progress in object detection definitely did not stop in 2015. It's just sort of difficult to measure continuous progress in this way because about that time, people switched over to start working on more challenging data sets. And the current state of the art on this Pascal VOC benchmark is well over 80%. I don't actually know what the current state of the art is because most methods don't even bother to test on this data set anymore since it's deemed to be fairly easy for object detection. So then last time we really focused on this RCNN family of models. We saw this slow RCNN that was sort of this first major jump over the non-deep learning methods. That was fairly slow, but gave fairly good results compared to everything else that had come before in object detection. And then we had seen this fast RCNN version that sort of swapped the order of convolution and pooling and gave some accuracy improvements, but even more importantly, gave some big speed gains. But I actually wanted to dive in a little bit more detail today on the training procedure for these RCNN style networks, because I realized that this is something we glossed over a little bit at the end of lecture. And then after class, a lot of students came up and asked questions, so I realized that this was just something that was not clearly discussed in the last lecture. And this should also serve as a nice recap of how these RCNN methods work as well. So remember in slow RCNN, the way that it works is that during training time, we're going to receive an RGB input, a single RGB input image, and during training time, we have access to the ground truth bounding boxes of this image, as well as the category labels for each of those bounding boxes. Now, then we'll run some region proposal method on top of our input image that will give us a set of region proposals on the image that tell us regions that are likely to contain objects. And again, we're just sort of treating this region proposal method as a black box because back in the days, people used to use things like selective search that were sort of heuristic methods, but later on, these got replaced by neural network methods as well. And this is basically all we had said last time about how we handle boxes in RCNN training. But there's actually another really important step here, which is that during each iteration of training, we need to decide whether each region proposal is either a positive, a negative, or a neutral region proposal. And we do this by comparing the region proposals that we get with the ground truth boxes here. So then here, now we've got kind of a lot of colored boxes going on in this image, so let's talk about them a little bit explicitly. So here, the bright green boxes are the ground truth bounding boxes of the three objects that we want to detect, being the two dogs and the cat. And now we get all of these region proposals here shown in cyan for all the different parts of the image. So we can see that some of the region proposals actually correspond pretty well to some of the ground truth objects. So in particular, we've got some region proposals that are very close to each of the two dogs and to the cat. But we also have some region proposals that we got maybe one region proposal on the face of the dog that partially intersects one of the ground truths, but is pretty far from being perfect. And we also got this region proposal in the background that covers this piece of a chair, which is totally disjoint from all of the positive objects that we wanted to detect. So now based on, then we need to categorize each of these region proposals as being a true positive, that is something relatively close to a ground truth region, and that would be these blue boxes, or I guess they're kind of purplish, but these blue boxes that are region proposals that are very close to a ground truth bounding box. And by very close, we usually measure that with some threshold on intersection over union. Now, some of the boxes are going to be, so these will be positive boxes that we want the network to classify as positive region proposals that do indeed contain an object. Some of the region proposals, however, will be negative samples that do not contain an object. So an example here would be this red bounding box in the background over the portion of the chair, because this region proposal does not cover any ground truth bounding box at all. And the way that we usually determine which bounding boxes are negative is also by setting a threshold on intersection over union. So here it would be common to say, for example, that a region proposal is considered negative if it has intersection over union less than 0.3 with all the other positive bounding boxes in the image, where that 0.3 would be a hyperparameter you would need to set via cross-validation. But interestingly, some of the region proposals are kind of in the middle. They're neither positive nor negative. So that's an example of that is this cyan cyan region proposal that we get over the face of the dog. So here it partially intersects a positive bounding box because it partially intersects the dog. So we don't really want to count it as a negative, but we also don't really want to count it as a positive because it's quite far from being a perfect bounding box. So actually we end up with these three different categories of region proposals based on matching them up with the ground truth. We get positives that should contain an object, negatives that definitely do not contain an object, and neutral boxes that are kind of somewhere in the middle. And now when we go ahead and train this thing, we're going to typically ignore the neutral boxes. And instead, we will train the CNN to classify the positive region proposals as positive and classify the negative region proposals as negative. Because trying to train the network on the neutral boxes would likely confuse it, since these are kind of boxes that are neither positive nor negative. So then when we train this thing, we will then tend to crop out all of the region proposals corresponding to crop out the pixels corresponding to all of the positive region proposals and all of the negative region proposals. And each of these boxes will just crop out the pixels of the image and then reshape them to be some fixed size, like 224 by 224, which is a standard resolution that we use in our classification networks. And then at this point, it basically looks like kind of an image classification problem, where rather than working on whole images, instead we're training on these crops that are coming out of these images. But once we've decided on these crops, then it looks basically like an image classification problem. So then each of these region proposals we pass into our convolutional neural network. Of course, we share the weights among all of these. And for each of these regions, we want to predict two things. One is a category label, and the other is a bounding box regression transform that transforms from the region proposal to the object bounding box that we should have predicted. So for the positive bounding boxes for the positive region proposals that did match up with some ground truth box, we know that they have a target category label which is equal to the category label of the ground truth box that they matched with. So that would be, for example, the dog, the two dogs, and the cat. And for the negative bounding box the negative region proposal that did not match with any ground truth box, we should classify it as a background region. And remember, we add this extra background region to our set of categories when we're doing object detection. And now the other wrinkle is on predicting the bounding box, because we see that these region proposals that are coming out of our region proposal method do not perfectly line up with the boxes of the objects that we wanted to predict. So then last time we talked about how we can parameterize this bounding box regression that transforms the raw bounding box coordinates into some target output bounding box that we actually will emit from the detector. Yeah, question? The question is, since we're using a black box region proposal method, how do we give the label to those proposals? Yeah, the positive negative label. Well, that really comes from this matching step. Because you imagine you kind of like set up a bipartite matching where you've got like all your region proposals over here and then all of your ground truth objects over here, and you need to kind of pair them up based on intersection over union between the region proposals and the ground truth boxes. So the label comes for because each positive region proposal ends up getting paired with the ground truth bounding box that it has the highest overlap with. So then we assign the category label to the region proposal based on the category label of the ground truth bounding box that it has the best match with. And that's the part that we like completely glossed over in last time's lecture. Is that a little bit more clear? So that gives us the label for the category label for each of these bounding boxes. But then there's also the trick of what should our regression label be. And now for each of these bounding boxes, because each positive bounding box, each positive region proposal had been paired with a ground truth bounding box, this lets us say what bounding box should we have predicted from this region proposal. So then we can use our the box transform target for the positive boxes will be the box transform that would have transformed from the coordinates of the raw region proposal into the coordinates of the bounding box that region proposal had been matched with in the input image. So that's a little bit subtle here because then it's kind of weird, right? Because the targets for each of these boxes depend on the ground truth box that we had matched the region proposals to. Yeah, was there another question? Yeah. So then we need to do this pairing up before training is one thing is something that you have to do. Although one thing that can get kind of tricky, so if you're doing this before training, then what we would typically do is run your region proposal method offline on your entire training set, and then do this matching up procedure offline. So because this matching is maybe kind of complicated, and if you have external region proposals, then you can actually do that offline and dump all these labels to disk before you start training. So that's one way that you might implement this kind of a method. Now, where it gets tricky is something like in faster RCNN, where we are now learning the region proposals jointly with the rest of the system. So then you need to do some of this matching online between the region proposals and the ground truth boxes. But that's only the case for something like faster RCNN, where we're actually learning the region proposals online during training. And then the other bit of wrinkle here is that for boxes that are negative, then it doesn't make sense to have any regression target, because a box that should have been classified as background was not paired to any ground truth bounding box. So for negative boxes, we do not have any regression loss. The regression loss is only applied to the region proposals that were marked as positive during this pairing up phase of the region proposals and the boxes. So that makes calculating your losses now a little bit more complicated than they have been in other applications, because now we have a classification loss for everything, but we have a regression loss only for some of the inputs to the network. And maybe the fraction of positives and negatives that you use per mini batch is now maybe another hyperparameter that you often need to set and tune when working with object detection methods. So this hopefully gives us a little bit more clear detail on exactly what the training time operations are when you're training one of these RCNN style networks. Yeah, question? Yeah, that's the idea. So then to kind of repeat that is that we're kind of making this assumption that RCNN is not inventing bounding boxes from scratch. The way that RCNN generates bounding boxes is by refining or perturbing the input region proposal boxes a little bit. So then during training, we kind of compute what transform would we need to do to snap the input bounding box, the input region proposal to a ground truth object bounding box, and that snapping transform becomes the target for the regression loss in RCNN. And now during test time, we also assume that we have region proposals that look similar as they did during training time. So then to get our final output boxes at test time, we run the same region proposal method on the image, and then apply these same regression transforms that are predicted per region proposal. Of course, this points to one obvious failure case of one of these systems is, what if the types of region proposals you use at test time are very different from the types of region proposals that you use during training time? Well, then you would of course expect the system to fail. Because one of the central assumptions of machine learning models is that the type of data we get as input at test time is similar to the type of data we get as input at training time. And for one of these RCNN style methods that rely on external region proposals, the region proposals are really part of the input to the machine learning method. They're not part of the output. So then it becomes very important that the statistics of the region proposals at test time are very similar to what they were at training time. Yeah. Yeah, the question is then how do you actually validate this? And that's why we use this metric of mean average precision that we talked about last time to evaluate object detection. And the problem is that like one way that you might imagine evaluating these things is like some accuracy style metric where I have some heuristic about maybe I extract a fixed set of boxes from each image and then see whether or not they match with the ground truth. But the reason why that's a difficult and bad way to evaluate for object detection is exactly, as you said, due to the large number of background boxes. So the reason that we use this mean average precision metric instead is that it helps us to factor out the effect of these large numbers of background boxes in a more robust way. So that's why we need this more complicated mean average precision metric when we evaluate object detection methods. Okay, so then the story here for fast RCNN training is basically exactly the same. So as you remember, the main difference between slow RCNN and fast RCNN is that we swap the order of feature extraction and cropping. So with slow RCNN, we were cropping independently the pixels from each region proposal, whereas in fast RCNN, we're going to run the entire input image through this backbone CNN and get these whole high-resolution image features. And then we will crop out the features corresponding to each of the region proposals from these image features. But other than this, and other than that, we still have the same procedure of pairing up the positives and the negatives, and all the training targets for fast RCNN are going to be exactly the same as they were in slow RCNN. And now for faster RCNN, remember that it's a two-stage method. That first, we have this region proposal network that's going to work on the backbone features and predict our region proposals. And then from there, we have this second stage that's going to crop the features from the region proposals and then make these final classification decisions. So with faster RCNN, one way that you can think about it is that we have two stages of transforming the boxes. In the first stage, we have these input anchors, and recall that the anchors are just these fixed set of boxes of fixed sizes and aspect ratios that are spread over the entire input image. And now in the first stage, what the region proposal network is doing is transforming this fixed set of anchor boxes into a set of region proposals. And now in the second stage, we want to transform the region proposals into our final output object boxes. And now the losses that we use at each of these two stages in faster RCNN is basically the exact same types of losses that we had used in slow and fast RCNN. That in order to transform anchors into region proposals, we need to do a similar type of pairing up effect. So in order to train the RPN in faster RCNN, this is where we're doing the transform from this fixed set of anchor boxes into these region proposals. And now again, we need to do the exact same pairing up, where for each anchor box, we need to say whether or not it should be a positive or should be a negative or should be a neutral. The only difference here is that rather than working on region proposals coming out of selective search, instead we're working on this fixed set of anchor boxes that we had specified as hyperparameters to the network. And the other difference here is that now in the region proposal network, we're only making a two-way classification. For each region proposal, or rather for each anchor box, we need to say whether or not it is positive or negative. And so then we don't need to give a category label in the region proposal network. We just want to say whether each anchor box should be classified as a positive region proposal or a negative region proposal. But other than that, we use the exact same logic for pairing up anchor boxes to ground truth regions, and the exact same logic for determining the classification labels and the regression targets in the region proposal network of faster RCNN. And then for the second stage in faster RCNN, it's exactly the same procedure again, where now we need to do a pairing up between the region proposals coming out of the RPN and the ground truth boxes in the image. And as we discussed a little bit earlier, now this part you actually need to do online, because the region proposals that come out for each image will change over the course of training, because we're jointly training the region proposal network with the second stage So that actually becomes kind of a tricky implementation detail as we move from fast to faster RCNN, is that now this pairing up between region proposals and ground truth boxes actually needs to happen online. But other than that, the logic is still the same, that we pair up our region proposals with our ground truth boxes, and after we pair them up, that gives us our classification targets and our regression targets for the second stage in faster RCNN. So hopefully this clears up, hopefully by walking through this a little bit more explicitly, this helps clear up a bit of the confusion from last time about exactly how these different networks are trained. Are there any more sort of lingering questions on these RCNN style methods? Okay, I'm sure more will come up later. Okay, so then there's another, remember the kind of one of the important new operators that we introduced as we moved from slow to fast RCNN was this feature cropping, right? Because in fast RCNN, we had swapped the order of convolution and cropping. And last time, right, the goal of feature cropping is that we need to do this cropping of the image features into region-based features in a way that is differentiable, so we can backpropagate through this whole procedure. In last lecture, we had talked about this ROI pool operation as one mechanism for cropping the feature vector, for cropping the features corresponding to regions. And recall that the way that ROI pool worked is that we take our region proposal from the image, we project the region proposal from the image onto the feature map, and then from there we snap the region proposal onto the grid cells of the feature map, because the feature map is probably going to be at a lower spatial resolution than the raw input image. And now another of these key goals of these cropping operations is that the output of the cropping operation needs to be a feature map of a fixed size so that we can feed the output of the cropping operation to our second stage network downstream. So in this example, we want the output to have a fixed spatial size of 2 by 2. So then in order to make the output have a fixed spatial size of 2 by 2, in the ROI pool operation, we're going to divide up the snapped region proposal into roughly equal sized regions, but they won't be exactly equal sized because after we divide up, we're also going to snap to the grid cells of the image features. And then within each of these sub-regions, these 2 by 2 sub-regions, we're going to do a max pooling operation. So this recall is this ROI pool operation that we talked about last time. So that lets us do this feature cropping in a way that lets us swap the order of cropping and feature computation. But there's actually a couple problems with the ROI pool operator. One is that these features are actually misaligned due to all the snapping. So there's actually two ways in which we're snapping onto the grid cells in ROI pool. One is that we take the whole region proposal and snap it onto grid cells. And then the other is that we divide up the region proposal and then snap the subdivided regions also onto grid cells. And because of these two bits of snapping, we actually end up with some misalignment in the features that are computed by this ROI pool operation. So now here we've kind of done a double projection, right? So here what's going on in the visualization is that the green box shows the original region proposal in the input image, and then we projected the original region proposal over onto the feature map, and then in the feature map we snapped it to this blue box and these different colored subregions, and now we're projecting the subregions back into the original input image. And now kind of the average position at which each of the features for the subregions is computed is going to be kind of the midpoint of these different colored subregions. So now we can see that due to the effects of these snapping, the centers of the subregions in the input image end up pretty misaligned with the actual input bounding box that we originally wanted to work with. And this misalignment is one big potential problem when we're working with, if we're going to use this ROI pool operation. And now there's another kind of subtle problem that seems a little bit weird with this ROI pool operation that is also related to the snapping. One way to look at what this cropping operation is doing is that it's a function that takes two inputs and produces one output. The two inputs are the feature map for the entire image and the coordinates of the bounding box at which we want to crop. And the output are the features for that bounding box. But now, because of the snapping, we cannot backpropagate to the coordinates of the bounding box, right? Because the coordinates of the bounding box were always snapped onto the grid cells of the feature map. So in this ROI pool operation, we can backpropagate from the region features back to the image features, but there's no way for us to backpropagate from the region features back to the coordinates of the bounding box at which we were doing this computation. So that also gives us a hint that maybe something is a little bit weird inside this ROI pool operation. Because normally we like to use operations that are fully differentiable and can properly pass gradients between all of the inputs and all of the outputs. And that's not the case with this ROI pool operation. So the fix for this is this ROI align operation that we did not have time last time to talk about in detail. But I wanted to go over it today because you actually will be implementing it on your homework in assignment 5. So it actually seems like something we should actually talk about in lecture. So the idea with ROI align is that we want to fix these problems that are we basically want to remove all of the snapping that's happening inside ROI pool. So the way that we're going to do this is make everything continuous, have no snapping anywhere inside the operation. So just as before, we're going to take our original input region proposal and project it onto the grid of features. And now, rather than doing any snapping, instead we're going to sample a fixed number of positions inside. We're going to divide the projected region proposal into equal-sized regions, and then within each of those equal-sized regions, we're going to have some equal-sized samples within each of those equal-sized regions. And these samples are the places at which we want to sample the image feature map. But the problem is that because we didn't have any snapping, the positions at which we want to sample these features probably do not align to grid cells, or probably do not align to the grid of the actual image features, right? So that's a problem. Right, the way that we normally think about doing this sampling is that you just want to pull out the features at one position in this grid of features. But now we kind of want to sample that feature map at arbitrary real valued positions arbitrary real valued spatial positions in that feature map. So now the way that we can do that is actually using bilinear interpolation to interpolate in between the cells of the grid of our image feature map. So kind of to zoom in on what that looks like for one sampled point so for one of these points we want to sample in this very lower right hand, so in the bottom right hand region, we wanted to sample 4 different points. And then we're going to zoom in at the bottom right hand point in the bottom right hand region to see what's going on there. So basically, we want to sample a feature vector from the image features at this real valued position 6.5, 5.8. But of course, it's a discrete grid, so we can't just pull out a feature vector at that point. But instead what we can do is do a locally linear approximation to the feature grid and sort of compute a feature vector at this real valued position as a linear combination of the nearest neighbor features that actually do appear in the spatial grid. And the particular way that we do this is bilinear interpolation, which means that in the x direction, we're going to look at the 2 nearest neighbor features in the x direction and have a linear blend a blend weight that scales linearly with the distance between the 2 nearest neighbor feature vectors in the x direction. And then similarly in the y direction, we're going to look at the 2 nearest neighbor feature vectors and blend linearly according to the distance between those. So to kind of walk through this a little bit more explicitly, in order to compute this feature vector at this real valued position, 6.5, 5.8, it's going to be some linear combination of these 4 nearest neighbor feature vectors that actually do fall onto integer valued positions of the grid. So then the way that we compute the linear weights on these 4 nearest neighbor feature vectors depends on the x and y distances between the point at which we want to sample and the actual positions in the grid. So now the weight for this feature vector at integer grid cell 6, 5, well, the x weight is going to be 0.5 because the position at which we want to sample is exactly in between 2 integer grid cells. And the weight for the vertical feature is going to be, and the vertical weight is going to be 0.8 because we're very close to this this grid cell. And then we kind of repeat this for each of these 4 nearest neighbor features in the spatial grid, where the linear weight for each of these 4 features depends on the distance between the actual position of the grid cell and the green position at which we want to sample. So then what we can see is that this is a differentiable operation. So we can backpropagate both from the right, because now during backpropagation, what we're going to do is we're going to get a feature, an upstream gradient for this sampled point, this sampled real valued point in the grid, and now we can backpropagate that upstream gradient both to the actual feature vectors in the grid, as well as the actual position of the bounding box. Because now the actual position of the actual real valued position of the bounding box was used to determine the spatial position at which we were going to sample. So we can actually backpropagate all the way into the coordinates of the bounding box that we received as input to this RY align operation. So this is now this differentiable operation that we can backpropagate through very nicely. And now basically we repeat this procedure. So within our region proposal, we're going to divide it up into equal size regions, and then within each of those equal size subregions, we're going to sample an equally spaced number of points within each subregion. And then once we've computed a feature vector for each of these green sampled points, this gives us now an equal number of feature vectors for each of our subregions. So now we can do max pooling on the sampled green points within each subregion to give the final feature vector to give one final feature vector for each of these subregions that then we can propagate forward into the rest of the network. And now I know this RY align operation was a little bit complicated, but it basically solves the two problems that we had with the RY pool operation. Now, because we have no snapping anywhere in this sampling procedure, because we're using real valued sampling and bilinear interpolation, now it means that all of our sampled features are going to be perfectly aligned to the positions in the input image. So it's going to solve this alignment problem that we had with RY pool. And it's also going to solve this differentiability problem with RY pool that we can now backpropagate upstream gradients both into the image feature map as well as into the positions of the bounding boxes that we had computed. And you guys will get a chance to implement this for yourself on assignment 5, so hopefully it will become clear by then. So that gives us kind of an overview of some of these object actually, I wanted to pause here to maybe let this sink in. Was there any questions on this RY align operation? Okay, there'll probably be questions on Piazza once we get to assignment 5. Oh, okay. So then, this returns us to the set of object detection methods that we had talked about last time. So remember we talked about this slow RCNN and fast RCNN, and now faster and single stage methods that no longer rely on external region proposals. But one kind of interesting question about faster and single stage object detection methods is that both of them still rely on some notion of anchor boxes, right? Because in faster RCNN, we had this fixed set of anchor boxes that we use inside the region proposal network, and in single stage detectors, we're still going to use anchor boxes, and we just make a classification decision directly for each of the input anchor boxes. So now there's kind of an interesting maybe thought exercise. Is there any way that we can design an object detection system that does not rely on anchor boxes at all, and just kind of more directly predicts bounding boxes in a nice, natural way? And there's actually a very cool paper that did this, that was done right here at University of Michigan in Professor Jiao Deng's group last year. And their really cool idea was this CornerNet architecture for object detection that is very different from all of the approaches to object detection that we've seen so far. I don't want to go too much into the details of this. I just want to give you a brief flavor of kind of what this does and how it's very different from the object detection methods that we've done previously. And this one will not be on the homework, so it's fine if you don't understand all the details. But the idea with this CornerNet architecture is that we're going to change the way we parameterize bounding boxes. And we're going to now represent bounding boxes by the upper left-hand corner and the lower right-hand corner. And now in order to detect a bounding box, we need to just simply have each pixel of the image decide what is the probability that I am the upper left-hand corner of each object category, and what is the probability that I am the lower right-hand corner of each object category. So then we're going to run the image through some backbone CNN to get image level features. And then from these image level features, we're going to predict an upper left corner heat map for each object category that we want to predict. So now this upper left corner heat map is going to say, for every position in the feature map, for every category that I wish to detect, what is the probability that this location in space is the upper left-hand corner of some bounding box at this point in space? And this you can sort of train with a per pixel cross entropy loss. And now similarly, we have the second branch that predicts for each position in space, for each category we want to detect, what is the probability that this position in space is the lower right-hand corner of some bounding box. And this you can also train with a cross-entropy loss. And now you can imagine training this thing, right? That I just say for every position in the feature map, should it predict either? We have targets for whether every position in space should be an upper left-hand corner and should be a lower right-hand corner. But now there's another problem, which is that at test time, how do we actually need to pair up each upper left-hand corner with some lower right-hand corner and to actually emit a bounding box. And the way that we overcome that problem is actually predicting also an embedding vector for every position in space. So for every position in space, we predict an upper left-hand corner embedding vector, and then in the right corner detection branch, we also emit a lower right corner embedding vector. And here the idea is that for each bounding box, the embedding vector predicted at its upper left-hand corner should be very similar to the embedding vector predicted at its lower right-hand corner. So then at test time, we can sort of use I'm hand-waving this part a little bit, but we can then use distances between these embedding vectors to now pair up each upper left-hand corner with some lower right-hand corner and now emit actually a set of bounding box outputs. So I thought this was a very clever and very cool approach to object detection that was very different from many of these other approaches that we've seen so far. And of course, it happened right here, so I got to talk about it. I just wanted to give you a brief sense of this very different flavor to object detection. And I'd also like to point out this was very recent. This was just published last year. So I think it remains to be seen whether this will become an important paradigm in object detection moving forward. But it's so different that maybe it could be, who knows. So that gives us some more details on object detection. And now we've got a couple other computer vision tasks that we need to talk about. So one is this task of, next up is this task of semantic segmentation. So to define the task, basically in semantic segmentation, what we want to do is label every pixel in the input image with a category label. So then for one of these input images of like this adorable kitten walking around on the grass, we want to label every pixel of that image as either kitten or grass or trees or sky or of whatever, given some fixed set of object categories that our system is aware of. And one important point to make about this semantic segmentation task is that it's not aware of different object instances. The only thing it does is label all the pixels in the image. So what that means is that if we've got two objects of the same category next to each other in the image, like these two cows in this example on the right, then semantic segmentation does not distinguish the two instances of the category. It simply labels all the pixels. So the output of semantic segmentation gives us this kind of like mutant brown blob, cow blob in the middle of the image, but it doesn't tell us which pixels belong to which cow, or even how many cows there are. So we'll overcome that with some later different tasks, but for now, this is the definition of the semantic segmentation task. And now one kind of maybe silly way you could imagine solving this semantic segmentation task is again using this idea of sliding windows. That you could imagine for every pixel in the image, we could extract a small patch around that pixel and then feed that patch to a CNN, and now that CNN could just predict a category label. And we could imagine extracting patches around every pixel in the image and repeating this over and over and over again. And this would be like very, very slow, very, very inefficient. This would be kind of the equivalent of slow RCNN, but for semantic segmentation. So of course, we definitely don't actually use this method in practice. But it's kind of instructive to think that this, in principle, should work pretty well given infinite amounts of computation. So instead what we do, what's very commonly used in semantic segmentation, is instead to use a CNN architecture called a fully convolutional network. And this is a convolutional network that does not have any fully connected layers or any kind of global pooling layers. It's just a big stack of convolution layers and all convolutional stuff. So then the input to the image is an image of some fixed spatial size, and the final output of the image is a set of class scores for every pixel. So as an example, you can imagine running this, you can imagine stacking a whole bunch of 3x3 stride 1, pad 1 convolutions, and then the output would have the same spatial size as the input. And now we want the final convolution in the final convolution layer in the network to have a number of output channels equal to the number of categories that we want to detect. And then we can interpret the output of this final convolutional layer as a score for each pixel in the image for each category that we want to detect. And then you could imagine doing a softmax over each of the scores at each pixel to give us a probability distribution over the category labels at each pixel in the image. And then we can train this thing using a cross-entropy loss per pixel. Yeah. Yeah, the question is, how do we know how many categories we have in the image? So here, whenever you're training a system for semantic segmentation, it's just like image classification in that we select a set of categories beforehand. And there's going to be some fixed set of categories that our system is going to be aware of. So then that will be determined by the data set on which you train. There'll be some set of categories that the data set has labels for. And then unlike object detection, we don't have any kind of variable sized output problem because we know a fixed number of object categories that the system is aware of, and then we simply want to make a prediction for every object category for every pixel. So then the output is, the size of the output is fully determined by the size of the input, and we don't have to worry about this variable output problem like we did in detection. So then we can imagine training this thing with a cross-entropy loss function per pixel, and then that should go quite nicely. But there's a couple problems with this sort of with this architecture I've actually drawn on the screen. One is that in order to make good semantic segmentation decisions, we actually might want to make decisions based on relatively large regions in the input image. So if we imagine stacking up a whole bunch of 3x3 convolutions with stride 1, pad 1, then the effective receptive field size is going to grow linearly with the number of convolution layers. Remember that if we stack two 3x3 convolutions on top of each other, then the output of those second 3x3 convolution is effectively looking at a 5x5 region in the input. And if we stack three 3x3 convolutions on top of each other, then the output is effectively looking at a 7x7 region in the input. So if you kind of generalize that argument, then you see that stacking a stack of L 3x3 convolutions on top of each other will give us an effective receptive field size of 1 plus 2L. And that means we would actually need a very large number of layers in order to get a very big receptive field size. And the other problem here is with computation. So in semantic segmentation, we'd often want to work on relatively high resolution images. And like people would sometimes apply this not just to like internet images, but also to like maybe satellite images that are like megapixels in all directions. So it's important that this be relatively computationally efficient. And doing all of this convolution at the original image resolution will be very problematic and very expensive computationally. So as a result, nobody actually uses architectures that look like this for semantic segmentation. Instead, you'll often see architectures that have more of this flavor, that use some kind of downsampling and then some kind of upsampling. And the advantages here are twofold. One is that by downsampling in the beginning of the network, we get a lot of computational gains just as we did in the image classification setting. And then similarly, by downsampling, it also allows our effective receptive field size to grow much more quickly as a result of these downsampling operations. And now downsampling we're very familiar with from convolutional neural networks for classification. We know that we can use something like pooling, either average or max pooling, or strided convolution to deal with downsampling inside a neural network model. But upsampling is something we really haven't talked about so much. And we don't really have any tools in our neural network bag of tricks that allow us to perform upsampling inside of a neural network. So then let's talk about a couple options that we can use for actually performing upsampling inside of a neural network. So because downsampling is often called pooling, then upsampling should clearly be unpooling, because it's like the opposite of pooling, right? So one option for unpooling is this so-called bed of nails unpooling. So here, given an input of spatial size, maybe C is the number of channels, and spatial size 2 by 2, we want to produce an output which is twice as large spatially with the same number of channels at each position. And now this is called a bed of nails unpooling, is because we're going to have the output be filled with all zeros, and then copy the feature vector for each region in the input, for each position in the input, into the upper left-hand corner of each corresponding region in the output. So that looks kind of like one of these like bed of nails that people lay on sometimes, that it's like 0 everywhere, and then we've got these feature vectors sticking up in kind of a grid-like pattern. This is actually not such a great idea. Probably leads to bad aliasing problems, so people don't actually use this too much in practice anymore. Another upsampling method or unpooling method that people use more commonly is nearest neighbor unpooling. So here we're just going to duplicate, so then each feature vector in the input is copied a fixed number of times to produce some larger output. So then this 2x2 input becomes a 4x4 output, and each position in the 2x2 input gets copied 4 times to give rise to a 2x2 region in the output. Now there's actually, remember we went through all this song and dance about bilinear interpolation inside the ROI align operation. And it turns out that we can also use bilinear interpolation for upsampling as well. So here, what we can do is we've got our input is now C channels and 2x2 in space. And we can imagine dropping a 4x4 grid of equally spaced sampling points in the input feature grid. And then for each of those points in the 4x4 sampling grid, we can use bilinear interpolation to compute these output features. And this is going to give maybe a more smooth version of upsampling compared to nearest neighbor upsampling. And if you're familiar with image processing, you know that another thing we can actually do is bicubic interpolation. So one way to think about bilinear interpolation is that we're using the one nearest neighbor in a little 2x2 region to compute a locally linear approximation to the input. And now with bicubic, instead what we're going to do is use a larger region in the input input feature map to compute a locally cubic approximation to the inputs, and then use that and then sort of sample according to this cubic approximation rather than a linear approximation. And I don't want to go into the details here, but this is basically basically whenever you resize an image in your web browser or an image editing program, it's usually using bicubic interpolation by default. And if it's good enough for resizing JPEG images to put on the web, then it's maybe a reasonable thing to try for resampling or resizing feature maps inside of your neural network. So these are all fairly simple approaches to upsampling, and they're all kind of implemented in standard frameworks like PyTorch or TensorFlow. Another slightly more exotic version of upsampling is kind of the opposite of max pooling. And this is, of course, it's because the opposite is called max unpooling. And the idea here is that now the unpooling operation is actually no longer going to be an independent operator in the network. Instead, each unpooling or upsampling operation will be tied to a corresponding downsampling operation that took place earlier in the network. So that gives, and then, so then when we do a max pooling operation to downsample, we're going to remember the position inside the grid where the max value occurred. And then when we do unpooling, we're going to do kind of like a bed of nails unpooling, except rather than placing each feature vector into the upper left-hand corner of the region, instead we're going to place it into the position where we found the max value in the corresponding downsampling max pooling region that happened earlier on in the network. And the reason that this might be kind of a good idea is that if you're training a network with max pooling, then in the forward pass of max pooling, you get this kind of like weird misalignment due to the max pooling selecting different points in the pooling region. And then if we unpool in the same way that matched the positions that we took the maxes from in the corresponding pooling operation, then we'll hopefully end up with better alignment between the feature vectors compared to something like bed of nails or bilinear. So kind of the rule of thumb here is that if in the downsampling portion you used something like average pooling, then for upsampling you should probably consider like nearest neighbor or bilinear or bicubic. But on the other hand, if your downsampling operation was max pooling, then you should probably consider max unpooling as your upsampling operation. So then which upsampling operator you choose kind of depends on your choice of which downsampling operator you had chosen in the other part of your network. So these are all options for upsampling that do not have any learnable parameters. These are all just fixed functions. There's no parameters that we need to learn for any of these upsampling operations. On the contrast, there's another upsampling operator that people use sometimes that is somehow a learnable form of upsampling. And that is called transposed convolution. And we'll see in a couple slides why it has this funny kind of name. But to kind of motivate transposed convolution, let's kind of remember how normal convolution works. So here, let's consider a 3x3 convolution with stride 1 and pad 1. So then we know that each position in the output is the result of a dot product between the filter and some spatial region in the input. And then because it's stride 1, we're going to move one position in the input for each position that we move in the output. Okay, this should be very familiar at this point, but it's just kind of walking through very, very clearly. Now let's change this to a stride 2 convolution. Then with stride 2 convolution, it's exactly the same, except because it's stride 2, we're going to move 2 pixels in the input for every 1 pixel that we move in the output. And now the stride kind of gives us a ratio between number of pixels that we move in the input and number of pixels that we move in the output. So then basically in normal convolution, when we set the stride greater than 1, we're going to end up downsampling the input feature map because of this ratio between the strides. But then is there some way that we could set the stride less than 1 and somehow stride multiple points in the output for every 1 point in the input? And if we could figure out a way to do that, that would be kind of like a learnable upsampling operation that we could learn with a convolution. And that operation is transposed convolution. And the way that it works is that now our input is going to be a low resolution thing of maybe 2 by 2 spatial size, and our output is going to be a higher resolution thing, here of maybe 4 by 4 spatial size. And then here, the way that the input interacts with the filter is going to be a little bit different. So here, we're going to take our 3 by 3 filter, and we're going to multiply the 3 by 3 filter by the input element in the input tensor. And that's going to be a scalar tensor product between the scalar value in the input and the filter value that we place in the output. And then we copy this weighted version of the filter into that position in the output. And then we're going to move two positions in the output as we move 1 position in the input. So now for this second position, what we're going to do is again take the filter value and now weight it by the second blue pixel in the input, and then multiply that pixel in the input by the filter value, and then copy the weighted filter into this moved position in the output. And then in these 2 regions where we have the outputs from 2 different filter values, we're going to sum where they overlap. And now if we kind of repeat this procedure over each of the 2 by 2 regions in the input, then we see that it gives rise to this kind of native 5 by 5 output, where that is like this overlapping sum of these 4 different 3 by 3 regions. And now we can actually get a 4 by 4 output by just like trimming one of the rows and one of the columns. And this trimming operation is kind of akin to padding in this transposed convolution operation. And now to make this a little bit more concrete, we can look at a concrete example in 1 dimension. So then here we're looking at transposed convolution in 1 dimension. So the input is a vector of length 2. The filter is going to be a filter of length 3. And then you can see that we are going to compute the output, what we're going to do is take the filter, x, y, z, multiply it by the first position, the first value a in the input, and then copy it into these 3 positions in the output. And then we're going to move 2 positions in the output for every 1 position that we move in the input. And now in the second position, we'll again take the filter value, weight it by the value of the input, and copy it into this moved position in the output. And then at this overlapping region, we will sum where these 2 things overlapped. Is this operation clear what's going on with transposed convolution? Okay. Now, actually, if you read different papers, you'll find that this operation goes by, different authors call it different things. Sometimes people call it deconvolution, which is like a really technically wrong name in my opinion, but you'll see that used in papers sometimes. People sometimes call it upconvolution, which is kind of catchy. People sometimes call it fractionally strided convolution, because it's kind of like a convolution with a fractional stride, which is kind of nice. People sometimes call it backward strided convolution, and this is because actually it turns out that this operation of transposed convolution forward pass is actually the same as the backward pass of a strided convolution. So that's actually a reasonable name. But the name that I think is that I like the best, and I think the community has converged on, is transposed convolution. Now, why the heck would we call this thing transposed convolution? Well, it turns out that because we can actually express convolution, the convolution operator, as a matrix multiply. So here we're showing an example in 1 dimension. So here we're showing the convolution between a 3 length vector x, x, y, z, and which is it should be XYZ, not XYX, as it is on the slide. I think I've had this typo on there for like 2 years. Okay, but this should be a vector XYZ that is a 3-length vector X, and convolving with this filter A, B, C, D. And you can see that the output here is going to be the normal convolution operator that we're familiar with zero padding. But what we can see is we can perform this whole convolution operation as a matrix multiply, where we need to duplicate the vector along the diagonal of the matrix on the left, and then we can do a matrix vector multiply between this matrix of copied portions of the input and this vector, which is the filter that we want to multiply with. And this lets us do convolution all in one matrix vector multiply. And now transposed convolution means we're going to do the exact same thing, except we're going to transpose our X matrix before we perform the matrix multiply operation. And if you look at the form of this matrix multiply, you can see that when we do convolution stride 1 and versus transposed convolution with stride 1, transposed convolution with stride 1 actually corresponds to a different sort of normal stride 1 convolution. And the way that we can see that is because the transposed data matrix X has the same kind of sparsity pattern in the transposed form as it did in the untransposed form. And what that means is that for stride 1, that convolution and transposed convolution are basically the exact same thing. Modulo maybe has slightly different rules for how padding works, but mathematically they're basically identical or equivalent. But now things get interesting when we consider stride greater than 1. So here we're showing an example of stride 2 convolution on the left being expressed as a matrix multiply. And now on the right, if we do a transposed convolution of this same operator, we can see that now the sparsity pattern in the transposed stride 2 data matrix is very different from, there's no way we could get this kind of sparsity pattern with any kind of striding pattern of normal convolution. So then this shows us that transposed convolution with stride greater than 1 actually corresponds to some new novel operator that we cannot express with normal convolution. And by the way, the fact that by looking at convolution in this way, it's kind of another easy way to maybe derive the backward pass for convolution. And in particular, looking at convolution this way makes it really easy to see that the forward pass of transposed convolution is the same as the backward pass as normal convolution. So it's kind of another nice symmetry between these two operators. So that's basically it for semantic segmentation, right? We know that we can build a network that involves some kind of downsampling and some kind of upsampling, and we talked about many different choices for upsampling, and then we use our loss function as our per pixel cross entropy. But of course, semantic segmentation is not really the end of it. So far we've talked about object detection that's going to detect individual object instances and draw bounding boxes around them. And we talked about semantic segmentation that's going to give per pixel labels, but it's not aware of different object instances. So you might wonder, is there some way that we can overcome this problem and kind of get these fine object boundaries as with semantic segmentation while also keeping the object identities as we have from object detection? Well, to talk about that, there's actually another bit of technical wrinkle here, which is that computer vision people often categorize object categories into two different types of object categories. One are thing object categories. So things are things that actually make sense to talk about instances. So like coffee cups or cans or dogs or cats or people, kind of awkward terminology, but I guess people are things in the mind of a computer vision researcher. But what that means is that a thing object category is one that it makes sense to talk about discrete object instances. And on the other hand, a stuff object category are more amorphous, and it doesn't make sense to talk about individual instances. So stuff would be objects like sky or grass or water or trees, where it doesn't make sense to talk about individual object instances, and instead they're just kind of like an amorphous blob of stuff in the image. So computer vision researchers often distinguish between these two types of object categories. And now this brings us to another distinction between object detection and semantic segmentation, which is that object detection only handles thing categories because it needs to distinguish individual object instances. On the other hand, semantic segmentation handles both things and stuff, but it doesn't care because it throws away the notion of object instances. So then kind of a hybrid task is that of instance segmentation, which is kind of like a joint object. We're going to jointly detect objects, and then for each object that we detect, we're going to output a segmentation mask for the detected object. And this instance segmentation task will only apply to thing categories because it only makes sense for types of objects that where we can talk about individual instances. So for example, running instance segmentation on these images of the two cows, we would get two detected cows, and for each detected cow, it would tell us which pixels of the image belong to each of the two cows. And kind of the approach here is going to be fairly straightforward. What we're going to do is do object detection, and then for each detected object, we're going to do semantic segmentation to determine which pixels of the detected object correspond to the object versus the background. So then to do this, we're going to build on our favorite object detector, faster RCNN. So remember that faster RCNN, I think you should be familiar with by now. And now to move from object detection to instance segmentation, it's going to get a new name. It's going to go from faster RCNN, now it's going to be called mask RCNN. But the main difference in the method is that we're just going to attach an extra branch or an extra head that works on the features of each region. That's going to now predict a foreground-background segmentation mask for each of the objects that we detect. And other than that, everything is going to be the same as object detection with faster RCNN. So then the way that this works is that we'll still take our input image, we'll run it through the backbone to get our image level features, we'll run our region proposal network to get our region proposals, and then we'll use ROI align to get these feature maps for each region proposal. And now for each region proposal, we'll basically run a little tiny semantic segmentation network that will predict a segmentation mask for each of our detected objects. And now you can imagine training this thing using now we're just sort of like jointly training object detection and semantic segmentation, where we're just doing a semantic segmentation for each object that we detect. So what this means is that now the training targets for these segmentation masks are going to be aligned to the bounding boxes of the region proposals. So then, for example, if our region proposal was this red box in the image, and the category we were trying to detect was chair, then the segmentation mask that would be our target for mask RCNN would be this foreground-background segmentation mask that was warped to fit within the chair bounding box. And had our region proposal been different, then our target segmentation mask for instance segmentation would have been different as well. And then similarly, if we were to try to detect maybe a couch, then the segmentation mask that we ask it to predict is going to depend on the category of the object. So the target segmentation mask for this red bounding box for the class couch would be the pixels of the pixels within the box that correspond to the couch class. And similarly, if we were detecting the person, then the target segmentation mask would be the pixels of the person within the bounding box. So that's basically it for mask RCNN. Like, you thought this was going to be challenging, but I mean, it turns out there's actually a lot of small details in the paper that matter a lot. But the big picture is that we're just basically attaching an extra head on top of our favorite mask RCNN system, on top of faster RCNN, to now predict an extra thing per region. And this actually gives like really good results when you train it up. So these are some actual predicted instance segmentation outputs from mask RCNN. So you can see that it's both jointly detecting bounding boxes using all the object detection machinery, and then for each bounding box, it's actually outputting this segmentation mask to say which pixels of the bounding box actually correspond to the detected object. So this works really well and is like a pretty good state-of-the-art, fairly close to state-of-the-art baseline for instance segmentation and object detection these days. Okay, now there's this other thing, instance segmentation we said only works on things, and semantic segmentation does things and stuff. Yeah, question? Yeah, so the question is, can we do instance sort of single stage instance segmentation? And that turns out there are a couple methods that work for that, but that's like very, very recent. So that's something that actually, I think the first like really successful single stage instance segmentation method was just published like a month ago. So that's something that people are like right now actively trying to figure out. So actually, remember like a couple weeks ago when you had guest lectures for a week? I was away at a conference, and actually there was like one of the first really successful single stage instance segmentation methods was presented at that conference. So this is like super hot off the presses stuff. So I wasn't quite comfortable yet to put it on slides. So yes, people are working on it, but I think it doesn't quite work super robustly yet. So then there's kind of a hybrid task that people work on sometimes called panoptic segmentation, which kind of blends semantic segmentation and instance segmentation. So the idea here is we want to label every pixel in the image, but for the thing categories, we actually want to distinguish the object instances. So I don't want to go into any details of how these methods work. I just want to give you this reference to let you know that this is a task that people sometimes work on. And I, again, don't want to tell you how it works, but some of these methods for panoptic segmentation actually work like really, really well. So these are now predicted outputs from a pretty high performance method for panoptic segmentation. So you can see that it's labeling all the pixels in the image, and for the thing categories, like the people and the zebra, it's actually disentangling the different instances. But for the stuff categories, like the grass or the trees or the road, then it's just giving us this amorphous blobs. So again, I don't want to go into details on this, just to give you a pointer to let you know that this is a thing that exists. So then another kind of cool task that people work on sometimes is keypoint estimation. So you saw here that we were able to output these segmentation masks for people. But for people, sometimes people want to have more interesting or fine-grained detail about the exact pose of people in images. So one way that we can frame this is as a keypoint estimation problem. So in addition to detecting all the people in the image, and in addition to saying which pixels belong to each person in the image, we might want to say like what is their pose and where are their arms and legs and how is their body situated in the image. And one way that we can formulate that is by defining a set of key points, like the ears and the nose and the eyes and all of the joints. And then we want to predict where are the locations of each person's joint, of each of these joints for each person in the image. And it turns out we can actually do this with mask-RCNN as well. So basically, to move from instance segmentation to keypoint estimation, we're just going to, again, attach an additional head on top of mask-RCNN that is going to predict these key points for each of our detected people in the image. So then the way that that works is that we have this same sort of formalism for mask-RCNN, except rather than predicting these semantic segmentation masks, instead we're going to predict a key point mask for each of the fixed number, for each of the k key points. So remember there's like 17 key points for the different body parts. So for each of those body parts, we're going to predict a key point segmentation mask. And then we can train these things up with a cross-entropy loss. And this actually, so I'm sort of intentionally going fast over some of these later examples. So these are things that I don't really expect you to know in detail, just to let you know what's out there. Then if we use this idea of key point estimation, now we can do joint object detection and key point estimation and instance segmentation all with a single mask-RCNN network. And these can give like really pretty amazing results. So it can detect all these people sitting in a classroom, and it tells us how many instances there are, and for each of those people, what is their exact pose in the image. And that actually works pretty well. So this is now this is kind of like a general idea, right? Is that anytime you want to have a computer vision task where you want to make sort of novel types of predictions for different regions in the input image, you can kind of frame it as an object detection task where you now attach an additional head onto an object detector that is going to make additional new types of outputs per region in the input image. So another cool example from Johnson et al. Is this idea of dense captioning. So here we actually want to merge object detection and image captioning, and then actually want to output a natural language description for lots of different regions in the input image. So this is a thing you can do by just following this paradigm of attaching now an LSTM or other kind of RNN captioning model on top of each region that is being processed by an object detector. And we don't have time to watch the video, but so then I kind of wrote this web demo that would like run the thing real time on a laptop and then stream it to a server. Then we could like walk around the lab and like watch in real time what kind of sentences were being described. So then you can see it's having a lot to say about my lab mate. This is actually Andrei Karpathy, who was my co-author on this paper. So you can see that it's detecting him as like man with a beard, man in a blue shirt. It's talking about the black monitor screen. So it like is doing joint object detection, and then for each detected region, it's now making a natural language description. So that's pretty cool. So then kind of another recent example, I mean, here I'm just like shamelessly promoting my own work. I hope you don't mind that too much. but kind of another kind of recent example from et al. Johnson is 3D shape prediction. So here we want to do joint object detection, and then for each predicted object, we actually want to predict a full 3D shape. So we can do this kind of following the exact same paradigm of doing an object detection system and then attaching this new additional head on top that works on top of each region and now predicts a 3D shape. And we'll talk in more details about we'll talk about more details about how to handle 3D shapes in next time's lecture. So then our summary from today is that we had kind of a whirlwind tour of a whole bunch of different computer vision tasks. Of these, I think object detection is the one that you'll be expected to know be most familiar with for the homework. But I think being aware of all these different computer vision tasks and just having a brief flavor of the fact that they exist and very briefly how they're done is kind of useful education when you consider applying different types of computer vision models in practice. So that was our whirlwind tour of a lot of different localization tasks in computer vision. And then next time, we'll talk more about how we can process 3D data with deep neural networks. And then we'll also see, for example, how to predict meshes with neural networks. So then come back on Wednesday, and we can talk about that.